Welcome back, friends, to another lecture on quantum field theory and quantum entanglement. In the previous lectures, we have been looking at uh, the quantization of the Dirac field essentially, and then in the previous lecture, I actually showed you that uh, the anti-commutator relations are the right way of proceeding towards the quantization of a Dirac field. If you use commutation relations, you end up with problems like negative norm states, or even if you somehow try to subside it and meaning just go forward, you end up having an Hamiltonian which is completely unbounded from below. These problems are essentially how not to meaning how not to quantize the Dirac field. This is okay. Just to quote verbatim from Peskin's book. Now, how to quantize it? We showed that if you assume, meaning if you impose uh, instead of commutation relations, if you impose anti-commutation relations of the type okay, of the type, so if you say psi bar of x, or okay, let's say psi of x anti-commutation psi of y, so that is equal to psi dagger of x psi dagger of y, this is equal to 0, and then psi of x psi dagger of y. This anti-commutation relation, let's put some spinorial indices delta alpha beta delta 3 x minus y. Okay. So if you impose these kind of anti-commutation relations on the field operators, which are essentially psi, this will in turn mean anti-commutation relations, so curly brackets again, of the type say B cap R. So things like this essentially B Q S on the raising and lowering operators. In the momentum space, essentially these are in momentum space. So in the raising and lowering operators, so there are two sets of operators B and C. So now you see that the anti-commutation relations don't have a relative negative sign. In the commutation relations, we had to impose the negative sign, otherwise you won't be able to satisfy the commutation relations for the C operators. You remember that, right? Essentially, and that itself will lead to you to problems. So in this case, we don't have to impose negative signs. Okay, so you have the same B, BB dagger and CC dagger. All other commutators vanish. All other anti-commutators, okay, so all the other anti-commutators vanish. So this is what we have seen, and this gives you a consistent Hamiltonian, and the Hamiltonian now has the picture that it is d cube of p 2 pi cube EP. So you can do the normal ordering, say for P, P, S, S, plus C, P, P, S, S, C dagger minus 2 pi cube a cube of 0. So once we do the normal order, I think we can throw away this term, goes to 0 in the normal order limit, goes to 0 in the normal. So this is what we have seen. Okay. Now, uh, so we say that this works very well. So this quantization works very well. Actually, how does it work? So if you build one particle states, there is no real how will you build one particle state? So you build one particle states by exactly the same way. Now what you say is that B and C annihilate the vacuum. The the annihilation operators B and C annihilate the vacuum. So this was the problem earlier. Essentially, we hadn't have this kind of an option earlier, but with anti-commutation relations, we have this option. Now this works it. So the annihilation operator defines the vacuum essentially. Okay. So what it does is if you it annihilates the vacuum to 0. Okay. And now so so even if you have anti-commutation, so if you look at now what happens is now you can start building one particle states by applying so a B dagger and C dagger. So if you have a B dagger of S, so you end up with say P, a state with P and a spin S essentially. So you can think of these are one particle states. Same thing for C operators also. But remember that one of them has negative energy and another has positive energy essentially. So you can build this tower of energy states essentially. Now, how do you know which one has negative energy and which one has positive energy? Remember that you can use the Hamiltonian. Which set of operators will have positive energy and negative energy? So you have Hamiltonian acting on Vp of R is equal to minus E P Vp of R and H Bp R dagger is equal to EP Bp R dagger. Okay. So the commutator with the Hamiltonian of the annihilation operator is negative of this. This just a negative of the energy with respect to the B operator, and the creation operator gives you positive energy. So this is clear, and same thing for C operators. And H of Cp dagger say R spin R is equal to EP Cp dagger R. Okay. So this commutation relations that we can always cover meaning tower of particles, and you also have if you want creating a particle with spinor u wave function, and then you will also have another momentum state with the C operators which contains a spinor V P R dagger acting on in P S, this creating a spinor V essentially creating an antiparticle with spinor V. So and the particle state tower and the antiparticle state tower are well behaved. You can see that essentially you can now okay okay. So you can construct this one particle states just like I have written essentially. Now the fun comes if you have two particle states, say n particle states, but we can always generalize it. But let's consider two particle states. So if you want to have P1 with a spin R1, P2 with a spin R2, a two particle state, you need to apply BP1 R1 dagger, BP2 R2 dagger on the vacuum. Okay. Now these operators, now what if I exchange P1 and P2, this should pick up a minus sign. So this will give me minus mod P2 R2 P1 R1. Okay. So this is obvious because you have anti-commutation relations. Okay. Okay, and which tells you that if you meaning you have anti-commutation relations, and this will obey, these particles obey, these particles obey obey Fermi Dirac statistics. So in particular, okay, in particular, if you have something like this, say P R, a state with same momenta and same spin, this is 0. And this is because of the Pauli exclusion principle. You cannot have states with the same quantum number, fermions with all quantum numbers same in the same state essentially. You cannot have particles with all same quantum numbers, two particles with all same quantum numbers in the same state. If the spin quantum number and the momentum quantum number are the same, you cannot put them in the same state essentially. Okay, so these particles obey Fermi-Dirac statistics, and so you can construct an n particle state, and which is like any meaning which such that with the exchange symmetry of two particles will always lead you a minus sign, essentially the fermionic minus sign. Now okay, good. So now that we have constructed the one particle, and so you can think of n particle states also, but remember that n particles you cannot put with the same quantum number in the same, okay, unlike bosons. Where we could keep n states of the same quantum number, meaning with you didn't care about the spin there essentially, where you could keep all the states essentially with the momenta in the same state. Okay, that is not possible with fermions. You need to have at least one of the quantum numbers different essentially. Unlike bosons, you cannot put any number of states with the same spin or same momenta into any number of particles into the same state. So this is clear. So these n particle states are different compared to bosonic n particle state. Fermionic n particle states are different. And this feature is implemented by quantizing the Dirac field using the anti-commutation relations. Okay, so far so good. Okay, using the anti-commutation relations. Okay, good. So now we are consistent that so you can build all these n particle states essentially with uh, Fermi-Dirac statistics by quantizing the fermionic field by using anti-commutator. So all well. So this is good. Now we can now start looking at correlation functions, endpoint green functions, and how do this, because we need this, right? Essentially, if you want to do in an interactive theory, we need to compute the Green's functions essentially, and we need to compute these Green's functions, which also essentially what we are looking at is computing the propagators essentially. Okay, now so again, remember the Heisenberg picture. So which we use for solving. Uh, if you solve the Heisenberg picture with the equation of motion, Heisenberg equation of motion, you get a mode expansion, right? Essentially, leads to mode expansion. So that is similar to here also, the same thing. This is what we saw in the scalar field. So we are going to do the same thing. So is equal to, maybe I should put the I on this side. Del psi by del t is equal to I h psi. So this is the Heisenberg equation of motion, and we solve this. How do we solve this? Essentially, we by putting the uh, mode expansion essentially. Okay, I already wrote the moment of p bar e power ipx. So for the particle, and then you also have the antiparticle essentially, which is c bar is dagger vs of p. Okay, let me use the same notation. Us of p. Okay, vs of p, then e power ipx. Okay, so this is a mode expansion. Now you want to put it back into the equation of Heisenberg equation of motion. Now, um, for doing that, I'll need to use psi dagger of x. So let me just write it down. Okay. Yes, p dagger u p s dagger e power ipx. So this is nothing but a conjugation of this one. So cps vs of p dagger e power minus ipx. Okay. Now with this, because we want to use this mode expansion in computing propagator, so we define the propagator in terms of anti-commutation relations. Essentially, again the same way, the propagator is also defined in terms of anti-commutation relation. It makes sense because the I think we have seen it in lectures, essentially other lectures of this course, that the propagator is sum of all the possible states essentially. So you have so you had to have anti-commutation, okay, of y. Okay, this is how you define your propagator. So the propagator, okay, we'll come to the Feynman propagator in coming on essentially. Okay. Now, the moment you see this, you know that this is a 4 by 4 matrix, because it is psi, which is a column, and then you have psi dagger, which is a row. So this is essentially a 4 by 4 matrix. So 4 times 1 times 1 times 4. So it's a 4 by 4 matrix. And this, let's calculate it, and we will see what it is. See, this is S. Now I want you to distinguish between SF and S. Essentially, there is no time ordering here as of now. So just substituting these modes into this relation and computing the anti-commutation relation, we'll end up having an anti-commutation between BP. Okay, this, and the second term would be with the V uh, spinors and C uh, ladder operators. So this will be, so it's obvious that you get these things, and so PS per P Q e power I uh, Px minus Qy. Now, imposing this anti-commutation relations, which we know, and then solving it. Okay, and then you will have one integral. Essentially, this will end up being integral d cube p 2 pi cube 1 by 2 EP finally you, and then you also have to use the outer products of the spinors essentially. So you also impose this BB bar anti-commutators, and then using outer products of the spinors, which we know are P slash plus M and P slash minus M. Yes, M. Okay, good. So this is your first look at the fermionic propagator. So this would mean okay. So this x minus y. So this is your first propagator. Okay, a fermionic propagator. Now what you can do some small tricks. So you can do some small reorganizations. So you can say you can use the equation of motion plus x times dx minus y. I'll define what is dx minus y minus dy minus x. Okay, I does slash plus m. Okay, I does slash pressure where d x minus y is equal to d cube p 2 pi cube 1 by 2 EP, and what is the remaining part, essentially e power pi minus ip x minus y. Now, in the scalar propagator, what we have seen is that this propagator has issues with meaning it should vanish off, right, for time like separations essentially. Okay, because we said that for space like events like separations, so that means x minus y square is negative. So d of in this case anyway, d of x minus y minus d of y minus x is equal to 0, and then we said that this commutator phi of x phi of y for scalar theory is equal to 0 for x minus y. Oh, x minus y square is negative. So in the bosonic theory, scalar field theory. So in scalar field theory, we said okay, it should vanish for space like separations, and then outside the light cone, right? Essentially, and that this theory was also causal and everything essentially. But in our case, in the fermionic case, instead of commutators, we have psi of x psi of y is equal to 0 for x minus y square negative. So for the space like separations essentially, for space like separations, the commutator doesn't vanish, essentially it's the anti-commutator which vanishes. Now, but now you may say why the commutator is not vanishing and all these issues essentially. So you can say that what you are actually going to say is that for all the observables, all observables essentially in fermions are always bilinears in the fermionic field, essentially are always in bilinears in fermionic field. So the causality is still conserved, causality still remains conserved essentially. Okay, these because all fermionic bilinears commute outside the light cone. That means all the bilinears you can think about. So you have psi bar psi at x times psi bar psi at y. This vanishes outside the light cone essentially. So the I think I guess you're I hope you're getting the point that we want the commutator also to vanish of the field variables essentially in terms of the fields, but it doesn't really matter for the fermions because what matters for the fermions are the bilinears because you cannot make any observable from fields essentially, but all the bilinears through which you can make all the bilinears, they commute outside the light cone essentially. So outside the light cone they commute, and so you say that okay, the causality is conserved essentially. Violated. Okay. So there is no real issue there essentially, but this is a subtle point which you should keep in mind. Okay, good. So finally, and now that we introduced the ordinary propagator, we should not be very far because we should introduce the ordinary as we have thought about. We should introduce the ordinary propagator, but that is not sufficient. We also need the time order propagator. Um, so we need the Feynman propagator. So okay, so okay, good. So we now move to Feynman propagator. Okay, good. So given this ordinary propagator, so I will stop here, and in the next class I'll start with the Feynman propagator, and then we'll look at the Feynman rules and for the free theory, and then we'll start doing interacting theories with the Dirac equation, with the Dirac fields essentially. Okay, just to recap, essentially we emphasized the role of anti-commutators, and then we showed that how to construct constructing n particle states automatically satisfies the Fermi Dirac statistics in this case. Okay, and so we showed the explicit example of for 2 particle states. You can do the same thing for n particle states, and you'll see that if we exchange any of these things, you'll end up having picking up a minus sign, and so the n particle states are automatically obeying Fermi Dirac statistics. And then we move to the Green's functions, and okay, and then we said that the mode expansion can also be okay done. Okay, anyway, so the mode expansion can also be motivated from the Heisenberg equation of motion, exactly like what happened in the scalar field theory. And then we define the propagator in terms of anti-commutation relations using, because we want to use the mode expansions in computing the anti-commutation and computing the propagator. The propagator here, which is not a vacuum expectation value, it is just the correlation function defined in terms of anti-commutation relations in this particular fashion. And so we have seen the properties of it, and we also questioned what happens outside the light cone. Okay, and we derived it, and we showed this is the equation of Green's function for this case. So let me stop here. So in the next class, I'll move to the Feynman propagator and other related aspects.